In this video, we will discuss various properties of functions, starting with even and odd functions. A function is said to be even if it satisfies the property that f of minus x is equal to f of x for all values of x in the domain of the function. A function is said to be odd if it satisfies the property that f of minus x is equal to minus f of x for all values of x in the domain of the function. For example, the function x squared minus 1 is an even function because when we substitute minus x in place of x, we get the same function back. Similarly, the function x cubed minus x is an odd function because when we substitute minus x in place of x, we get the negative of the function back. We can also tell if a function is even or odd by looking at its graph. If a graph is symmetric about the y-axis, then the function is even. And as you can see, the graph of this function is indeed symmetric about the y-axis. If you are not familiar with the concept of symmetry, please refer to the second video in this playlist. We have covered this topic in detail in that video. The link to the video is provided in the description below. Similarly, if a graph is symmetric about the origin, then the function is odd. And as you can see, the graph of this function is indeed symmetric about the origin. Let's now move on to the next property of functions, which is increasing, decreasing, and constant functions. A function is said to be increasing if the value of the function at x1 is less than the value of the function at x2 for all values of x1 less than x2. Let's take an example to understand this concept better. If we plot this function, we can see that the function is increasing because the value of the function at any value of x is less than the value of the function at any greater value of x. Also, the slope of the function is positive, which is another indicator that the function is increasing. A function is said to be decreasing if the value of the function at x1 is greater than the value of the function at x2 for all values of x1 less than x2. Here is an example of a decreasing function. The value of the function at any value of x is greater than the value of the function at any greater value of x. Also, the slope of the function is negative, which is another indicator that the function is decreasing. Finally, a function is said to be constant if the value of the function at x1 is equal to the value of the function at x2 for all values of x1 less than x2. As you can see in this example, the value of the function at any value of x is equal to the value of the function at any greater value of x. The slope of the function will be 0 for a constant function. Also, do not think that a function can be only increasing or decreasing. A function can be both increasing and decreasing over different intervals. Take this function for example. The function is decreasing from negative infinity to 0 and increasing from 0 to positive infinity. Now let's discuss the concept of maxima and minima of a function. Maxima and minima of a function are the points on the graph of the function where the function attains its maximum and minimum values respectively. A local maximum is a point on the graph where the function attains a higher value than its neighboring points in the open interval around the point. It means if you move a little to the right or left of the point, the value of the function will be less than the value at that point. Similarly, a local minimum is a point on the graph where the function attains a lower value than its neighboring points in the open interval around the point. It means if you move a little to the right or left of the point, the value of the function will be greater than the value at that point. Absolute maxima and minima, on the other hand, are the points on the graph where the function attains the highest and lowest values, respectively, over the entire domain of the function. So do not confuse between local and absolute. The local maxima and minima are the highest and lowest points in the open interval around the point, whereas the absolute maxima and minima are the highest and lowest points over the entire domain of the function. Finally, let's talk about the concept of piecewise functions. So far, we have discussed functions that are defined by a single equation, but sometimes a function can be defined by different equations over different intervals. Take a look at this function, for example. The functions that are defined over different intervals with different set of equations are called piecewise functions. The way we graph a piecewise function is by graphing each segment of the function separately over the interval as if it were a separate function. The open circle indicates that the function is not defined at that point. The closed circle indicates that the function is defined at that point. Note the gaps in the graph between the segments. When there are gaps in the graph, we call the function discontinuous at that point. You may be wondering if all piecewise functions are discontinuous. The answer is no. A piecewise function can be continuous as well. Take this example for instance. The function is continuous at the transition point even though it is defined by different equations over different intervals. I hope you were able to follow along with the video. I know it was a lot of information to take in, but don't worry if you did not understand everything. We will be reiterating these concepts in the upcoming videos when we look at different types of equations and their graphs. So that's all for this video. If you find this video helpful, please like, share, and subscribe to the channel. This will help us in reaching out to more students. In the next video, we will look at quadratic functions. Thank you for watching.